Okay, December 2nd, 2021, and Physics 37 at the Los Angeles Harbor College. Okay, so we're talking about universal law of gravitation. That's due to Isaac Newton. There are, so far we have covered three laws, three Newton's laws. One of them is not a law. First Newton's law is not exactly a law because it's a consequence of second law, and there's the law of action and reaction. Then there is this other law that's also credited to Newton himself. He came up with a solution at that time, and people were after him to asking him to explain. It's a nice story, you know. There is this guy called Edmund Halley. Okay, Edmund Halley, and that's veridical. Everybody heard about the Halley comet, right? So it was him who, it was Edmund Halley, right, that predicted the appearance of the comet that ended up being taking his name. But in reality, it was Newton that helped him calculate the orbit of this comet that was showing up every now and then, every 70 something years. Okay, so Edmund Halley came to Newton and said, look, there is this comet that seems to be the same one. It appears every 70 and something years, and it's about time for it to show up again, you know. And I'm trying to figure out how Edmund Halley asked Newton, right? How to predict the exact position of that comet knowing what we knew from previous observations, right? And Newton came around and said to him, oh yeah, this problem I solved 20 years ago. He said, you solved this problem 20 years ago and didn't tell anybody about it? Newton was very secretive about his work, okay? He would write things that in his book he'd put aside, in his journal would keep it a secret. You know, people that keep secret, things under secret so they can have an advantage over their competition, right? So that's what Newton would do. And then Edmund Halley finally convinced Newton to disclose all the steps that would take to calculate the orbit of the comet. So what we are going to do here is to give just the very basic principles. Okay, we're not going to calculate the orbit of the comet Halley. Okay, we're going to just give you the very basic principles that serves as a foundation for what Newton did at that time. So what he discovered was that if you have a mass, you know, in space, just like this mass 1, and you have a second mass m2. Okay, so what did he discover? He discovered that, and those two masses are separated by a distance d. He discovered that the second mass exerts a force on the first mass. Okay, so this notation here, go ahead, spell that out, this notation. This notation is force in 1 due to mass number 2. Okay, that's what it means. Here you go. I'm gonna write it down here. Force in 1 F12 is force in mass 1 due to mass number 2. Force in mass number 1. That's what this notation means. And I'm going to increase the size here. Let's get this. Subscript. What else? And let me copy this guy here. So he found that the masses attract one another. Not only you have this force applied to mass number 1, but where you also have this force applied to mass number 2 due to mass number 1. Okay, so now, here you go. Just go back to Newton's third law of motion. force in mass number 2 due to mass number 1. Go back to Newton's third law of motion, right? If two objects interact with one another, the force that one exerts in the other is equal in magnitude and opposite in direction. Okay, you can see that F12 is equal to minus F21. Here we go. I'm gonna write that down here. Oh, this one. Let me see if it's in the next slide. No, it's not. So I'm gonna put it here. Oops. Go down. F12 is equal. Put to F21. You don't even need Newton's universal gravitational law to know that stuff. This one I suppose. Let's see here. Yeah, okay, good. Here we go. Minus. Okay? And that comes to Newton's third law. This law of universal gravitation must be compatible with Newton's third law. Okay? And this is a vectorial force. This is a vectorial force. So, what's the relationship for those guys? Okay, there is a simple relationship. It's given by that, by this formula here. The force decreases the square of the distance, and this force is attractive. Okay, it is directly proportional to the masses, m1 and m2, inversely proportional to the square of the distance. What you see right in here is a constant, a universal constant that we know the value. That's just the vectorial format. Let me see if I have G here. Big G, big G. Okay, that's the value of big G. It's a very small value. See that? 10 to minus 11. It's a very small value. So because big G is a very small value, the force of attraction is going to be perceptible, is going to be measurable only for very massive objects like planets and moons. Okay, we do have a mass and we do attract each other here in the classroom, but because of this very small proportionality constant, this force is so small, this force of attraction between us here is so small that we cannot even measure. Okay, so but we can calculate, for instance, the gravitational force of on a 80 kilogram mass that's over the surface of the Earth. Okay, let's do that. And you're going to see that this value is approximately 800 newtons. Okay, so here you go. What we do, you have someone sitting on the surface of the Earth. So let me check if I have a no, I don't have it. Okay. Oh yeah, I have it here. Here you go. That's the illustration that I want to show you. Someone is sitting down on the surface of the Earth, and that's 80 kilogram mass. And because of the law of universal gravitation, it's being attracted towards the center of the Earth. This thing here can be illustrated as two masses, right? The mass of the Earth and the mass of the individual, or the mass of the object. And they are separated by a distance that's equal to the radius of the Earth. Can you picture that? The radius of the Earth is a quantity that had been measured back in 200 BC, by the way. Okay, there was this genius there, Eratosthenes, in ancient Greece, who figured out a way to measure the size of the Earth at that time. Okay, and then there was another genius there at that time, which was Aristarchus of Samos, that managed to measure the distance from the Earth to the Moon. It was about at the same time of Eratosthenes. So those things have already been known for a long time. Some things have already been known for a long time. The size of the Earth, for instance, and the distance from the Earth to the Moon. Okay? Aristarchus of Samos tried to measure the distance from the Earth to the Sun using a technique that was correct, but he didn't have the instrumentation, the proper instrumentation to achieve an accurate measurement for the distance from the Earth to the Sun. The Sun is so distant from the Earth that he didn't have the proper equipment to come up with an accurate measurement, but he was able to get a very good measurement of the distance from the Earth to the Moon. And Eratosthenes later on managed to get a distance the size of the Earth, managed to get a measurement of the size of the Earth. Okay, and the size and the radius of the Earth is approximately 6,500 kilometers. The radius. Let me see what about 6,300, 6,370 kilometers. Okay, so when you plug in everything, what you have to know? You have to know the mass, 80 kilograms, and you have to know the mass of the Earth. Okay, the mass of the Earth you can find out from any book in physics, and there is a smart way of measuring that. It's not easy. The measurement of the mass of the Earth was done only very late on. It was around the 1700s. Okay, in the 18th century. After Newton, by the way, Newton himself didn't know what was the mass of the Earth when he formulated his theory of universal gravitation. So you go ahead, substitute the value for big G. The mass one is 80 kilograms. The mass of the Earth is this value here, which is approximately 6 times 10 to 24. Okay, and the radius of the Earth is 6,370 kilometers. You square it, and then what do you get? Do the math, do the math, do the math. You get 785.5 newtons, which is very close to 800 newtons. Okay? Very close to 800 newtons, which is 800 newtons we get when we use mg, g for equal to 10 meters per second square, right? So here we got 15 newtons difference, 14 newtons difference. Okay, 14 newtons difference must be 2% difference, must be 2%. Let me see. Yeah, that's right, it's 2% difference. Okay, so if you want to get this value here, you get 80 kilograms and multiply by 9.8. If you multiply 80 by 9.8, you get this value right in here. Okay, and that's what we did. We found the same result using a more genetic equation. We didn't use mg. We used something far more genetic, which is Newton's universal law of gravitation. Okay, big G, m1, m2 are square. Okay, now what this other example is all about? This other example is about two masses of 80 kilograms separated by a distance of 1 meter. What's the gravitational force between each other, right? Remember, we got approximately 800 newtons because the Earth is a huge mass. It's a huge mass. But what happens if we substitute the mass of the Earth by 80 kilogram mass, by 80 kilogram mass? Of course, we have to cut down the distance, right? It's going to be 1 meter only. So let's see what we get. That's what the next example is all about. Here you go, plugging out the numbers. M1 is 8 kilograms, M2 is 80 kilograms, the distance is 1 meter, and we still have this small value, 10 to minus 11. When you crank up the values, you get what? We have this very small force on the order of micronewtons, less than micronewtons, 0.4 micronewtons. 4 times 10 to minus 7 newtons. It's very difficult to measure this type of force. So we do attract one another, like I said here, but the force is so small that we can hardly feel. Okay, let's see, and then we have this other, okay, gravitational force is a vectorial force, right? So we have like this other example, 3 objects, 80 kilograms, disposed on the same plane. They are separated, 1 and 2 objects, 1 and 2 are separated by 1 meter, and 1 and 3 are separated, okay? Objects 1 and 2 are separated by distance 1 meter, and objects 1 and 3 are also, objects 1 and 2 are, okay, same distance. And they make like a right angle triangle. What's the net gravitational force on object 1? Okay, let me see if I have, I don't have an illustration here. Let me see if I have right in here. That's a shame. No, I don't have it, unfortunately. Okay, so it's easy to picture, okay? Let me see if I can do that for you. Uh, I'm gonna get this one here. Oh, I'm gonna draw in the. No, it's okay. I'm gonna draw here in this guy. Here. Yeah. Okay. The situation is the following. Because forces are vectorial in nature, they obey that principle that we call the superposition principle. Superposition principle means what? It means that the forces act add vectorially. The gravitational force acts vectorially. Okay? Add vectorially. So this situation is like that. Let me shrink this object as much as I can. Let's see if I can do that. Yeah, that's one of the masses. That should be mass 1. It's separated by 1 meter from mass 2 and another meter from mass 3. That's how you illustrate the problem. Because of the mass, here you go. 3 objects, 80 kilograms. They all have the same mass. They make a right angle triangle. They are both separated the same distance. Okay, it's like that. Oh, this one. This one here. I'm gonna get rid of the rest. Let's see here. They all have the same mass. This one right in here. Because they have the same mass, I label them with the same letter. I don't need anything else. Whoops, right in here. Right in here. Okay. Go a little bit down. Oops. Like that. So let me see if I can get another. Okay, I'm gonna get this vector here. Gotta be a different color so we can see. So what's happening here? You know, that's mass 1, that's mass 2, that's 3. Mass 2 is attracting mass 1, like that. So this force I will call force of 1, force in 1 due to 2. 1, 2. Okay? And in addition to that, we also have this other force that's due to mass number 3. Oops, that. Good. Force in 1, 2, 2, 3. That's a type of drawings that you have to make when you solve this problem. Why keep on moving? Strange. Okay. Similarly, we have the reaction force here, right? F of in 3 due to 1, F in 2 due to 1. But I want to know the net force applied to mass 1. The net force applied to mass 1 is going to be the vectorial sum of those two forces. Or let's say what we call, right? Vectorial, the net force. Like that, there. Oops. Right, I'm summing that up. I want to make a very realistic net force. Maybe like that. Like that. That's the net force on 1. I will label it F1. That's what we call the superposition principle. Okay. So we go ahead and calculate each of those forces. Here I changed the notation, okay? Here I changed the notation. I'm saying force of 2 in 1, okay? Force of 3 in 1. Those two forces are going to be equal because the distance between the masses is the same and the values of the masses are the same too, okay? So when you substitute 80 kilograms here, 80 kilograms here, and 1 meter here. Oh, by the way, we calculated that before, right? We calculated that before. You got 4.27 times 10 to minus 7. Okay? And don't forget here I changed the notation. F31 means force of 3 applied to 1. It's just a matter of definition. And then the net force is going to be what? The net force is going to be due to the Pythagorean theorem. Square root of the sum of the squares. Okay, when you do the sum of the squares, you get the square root of 2. Square root of 2 is 1.41, and then you go ahead and put the numerical value of the F force. The angle is going to be 45 degrees. Okay? The angle is going to be 45 degrees. What else you have to know? You have to know about the gravitational acceleration. Okay? Here you go. An object that's nearby the Earth's surface is subjected to this force here, where big M is the force of the mass of the Earth, small m is the mass of the object. R, big R, here is the radius of the Earth. Okay, so this equation can be rewritten as being mg. Okay, where this little m is this guy right here, and the g, which is the acceleration of gravity, is going to be given by the big G, big M, R square. That's how we find out the acceleration of gravity. Here you go. Right in here. If you go ahead and do the math, you get 9.8 meters per second square using the radius of the Earth, using the mass of the Earth, okay? If you want to know the variation of the acceleration of acceleration of gravity with the height, you can go ahead and replace the r here with r plus h, where h is the height above the surface of the Earth. Okay, as we move away from the Earth's surface, the acceleration of gravity decreases slightly. Okay. Consequently, the weight of the individual also decreases slightly. And that's what you end up getting for the acceleration of gravity. Let me see if I have some values here. I don't have a value, unfortunately. Huh. Yeah, I could do the table here in Excel for you, so you have an idea what happens. Let me get the table here, Excel. I'm going to write down an equation for you. Zoom in, yep. We're going to write down the value of big G. We're going to write down the value of big M. We're going to write down the value of the radius of the Earth. And we're going to calculate the acceleration of gravity in terms of those terms. Here you go, and Mr. per second square. Okay, here we're gonna put everything in meter, just like we do in the lab. The mass is in kilograms. I'm not gonna put the unit for big G. It's too much work. It's too much work to put the unit for big G, okay? So here you go. Big G is what? 6.67, right? Have you memorized that? 6.67 times 10 to minus what? 11. 6.67 times 10 to minus 11. Go. 6.67, 10 to minus 11. The mass of the Earth is what? The mass of Earth is 6 times 10 to the 24, right? 6, yeah, here, right in here. Almost 6. 5.97. I'm going to put 6 times 10 to 24 kilograms. And the radius of the Earth, we saw that before. 6.37 times 10 to the 6. 6.37 times 10 to the 6. Yeah, it is, right? Yeah, times 10 to the 6. And now we are going to, all those are going to be constants. And I'm going to write down the equation. By the way, we're going to start at height 0. And little by little, we are going to increase the height. The equation for the acceleration of gravity is going to be big G times big M divided by R plus H square, like that. See the value of the acceleration of gravity here? 9.86 at the surface of the Earth. I'm going to change the format. Number. I'm going to put this as a number. We don't need to keep it because it's better this way. I don't want this one. Let me see. Yeah, I will leave this one like that. Everything else is better to leave in exponential notation, scientific notation. Okay, and what else I'm gonna do? Okay, I gotta put a dollar sign here. I forgot to do that. Dollar sign here. There's a reason why I put a dollar sign here, but I don't put a dollar sign in the other one, in the E. Okay. So we are going to do the following. For we are going to calculate the acceleration of gravity for every 10,000 meters. 10,000 meters is 30,000 feet. 30,000 feet is the altitude that airlines fly. Every time that you take a flight to the East Coast, the airplane is flying at 10,000 meters or 30,000 feet. Okay, and then we're going to calculate the acceleration of gravity at that spot. Here you go. See, there's a very small decrease in the acceleration of gravity. Your weight is a little bit less, but it's very small. You can hardly see the difference. We are talking about 3 out of 900, 3 out of 10. 10 wait a minute, 3 out of 10, that's right. Oh, wait a minute. 3.03 out of 10. 0.03 out of 10 is 0.3%. Okay? It's 0.3%. It's negligible. Go ahead and calculate for higher altitudes. 10,000 feet, 20,000 feet. Let's see here. Click and drag. So, as we increase in altitude, here is 60,000 meters. 60,000 meters is 180,000 feet. That's the altitude of the Concorde. No, wait a minute. Concorde was 60,000 feet. It's even higher than Concorde. It's 3 times higher. 60,000 feet is 60 kilometers. It's just below the altitude that which one flew that? Which was Richard Branson. Yeah, Richard Branson flew with his spacecraft too. Remember that? Just recently. It's just below. Richard Branson flew just above this line, 60,000 meters. Okay, and keep on watching what happens. Let's see. We are right in here. We are 100 kilometers. 300 kilometers high. Okay, that's where space starts, according to the International Astronautical Federation, IAF. The acceleration of gravity decreased from 9.8 to 9.56. Okay, and the higher you go, the lower the acceleration of gravity becomes. Let me see. Here we are 400 kilometers now. 400 kilometers, which is the altitude of the space station. Space station altitude varies somewhere between 300 to 600 kilometers. See, the acceleration of gravity decreased from 9.8 to 8.7. Okay, and so on. So let's plot this graph. Let's plot this graph, and we are plotting against the height. The height from the surface of the Earth. Oh, see, looks like a linear decrease, right? Looks like, but that's because the format of the graph is not a good one. Let me get this thing 7.5 here. Maybe we'll start to see, or maybe you won't. Yeah, it still looks like a linear decrease, right? It's not linear, but it looks like a linear decrease because we're getting a very small section of the graph. Okay? It looks like there's a little bit of a curvature here, right? But we can start seeing the curvature in a better way if we get more data points to our graph. There you go. Instead of stopping at what? I stop at 900 kilometers. Let's go even higher than that. 900 kilometers, let's see. 5,000, 6,000, 7,000 kilometers. Okay, it's very low. This altitude is still considered very low. 10,000, 13,000, 15,000, 16,000. And then we're going to plot that. 20,000. The altitude of, there is a very important altitude out there, but I'm going to stop here, otherwise it's going to be too much. Let's plot the graph now. Hopefully we'll be able to see the curvature in the graph now. Yeah, now you see the curvature, right? It's decreasing. This is the square of the distance. In the previous graph, you see, it looks like a straight line, but it looks like a straight line because we are getting just a small section of this graph right in here, right? So that's how the acceleration of gravity varies at this altitude of, let's see, 27,000, the acceleration of gravity is very small, it's 0.35. Okay, from 9.8 to 0.35 meters per second square. So that's how it behaves. Okay, and let's see, we did this one, right? Acceleration of gravity. Okay, we're not gonna do Kepler's law because we didn't cover Kepler's law. It's an important, anyway, it's an important law. Okay, okay, okay. We are gonna do this interesting problem. Okay, a geosynchronous satellite. Have you heard of the geosynchronous satellite? There are low Earth orbit satellites and there are geosynchronous satellites. The space station is in low Earth orbit. Low Earth orbit somewhere between 200 kilometers to 1,000 kilometers. Okay, then there is medium Earth orbit as well. And there is a class of satellites that are located in this spot at this specific distance from the center of the Earth. Okay, and those satellites at this spot has a very important practical application. Yeah.
So ground speed is 0.
What did you say?
The ground speed is 0.
Ground speed with respect to the Earth, right? Yeah, that's right. So there is even another way also to mention that, right? All the stars, let's see, where is the north here? North, north, north. Which way is north? That way? Okay. That way is the north, right? So that's east, that's west, right? So the stars rise on the east, they take this path here in the sky, and they set in the west. They don't go like that. The stars in the sky, they go like in an inclined path. Okay, depending on the latitude of the place, they go just like that. Okay, so as time goes by, the stars rise in the east and set in the west. So if you put a spacecraft at a specific distance from the Earth, okay, the spacecraft is going to stay at the same spot all the time. Okay, those are the geosynchronous satellites. Just like Robert said, the ground speed of the satellite, yeah, relative to the Earth's surface is 0. Okay, yeah, but the satellite is still orbiting the Earth. Okay, but remember, ground speed is a relative motion. With respect to the Earth, yes, it is at rest, to the surface of the Earth. But with respect to the center of the Earth, it is moving around the center of the Earth. Yeah.
What's the velocity of the geosynchronous satellite?
Ah, we can calculate that. We can calculate that. Let's do that. Let's see. Again, you gotta be velocity with respect to what, right? You gotta ask yourself. With respect to this, in this case, should be the velocity of the satellite with respect to the ground is 0, just like Robert said. But the velocity of the satellite with respect to the center of the Earth is not 0, and we can calculate that. Okay? Because the center of the Earth is not rotating, right? The center of the Earth doesn't have a tangential velocity, right? Like that. Here you go. Here's the center of the Earth, right? Everybody here is moving with respect to the center. Here's the equator. We all have a tangential velocity with respect to the center of the Earth. Here you go. Okay. And we can calculate that. But first, let's calculate what is the. Let me see. Adjustment is a satellite equal to. We want to find out his altitude. Okay. So here goes. It's like that. We have the Earth right in here, somewhere around here. We're going to calculate this distance. Here we are sitting here on the surface of the Earth, right? So after, let's say, how many hours? 24 divided by 4. After 6 hours, we move from here to here, right? Can you picture that? And then after 6 hours, the satellite too moved from here to here. It's not that the satellite is at rest. The satellite is moving, okay? Satellite is at rest with respect to the Earth's surface, but not with respect to the center of the Earth, right? The satellite is just synchronized with the rotation of the Earth. See, like that. Okay, better this way. No, not too much. And that's what we call, and then a geosynchronous satellite takes 24 hours to, revolve around the center of the Earth. Just like the Earth takes 24 hours to move around its axis, right? A full. So we can calculate that, and let's do that. Here we go. I'll do this step by step. Let's see. Uh, let me see if I can have a. Let me see if I have an illustration here. Oh yeah, right in here. That's the illustration that you have to do. Here's the Earth. Here's the orbit of the satellite. Okay. And I'm gonna put something else too. Okay. I assume the satellite moves. Oh, circular orbit. Assuming the satellite moves in a circular orbit around the Earth, around the Earth, find its altitude. Oh, not what I want. This one here I want. Okay. So you have to go ahead and do your free body diagram. The free body diagram is this one right in here. We're gonna zoom in into the satellite. Okay, and you're going to find out the forces. There is only this force here being applied to the satellite. Only the force of gravity due to the Earth. And I can write that down. Now I'm gonna do the step by step. Physics notes. Let's see, physics note right in here. Go, 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 go. Okay, so we go. We're gonna go to the bottom right in here. Oh gosh. What a slow computer. Yeah, I didn't take any notes last time. Here you go. So the force on the satellite. Satellite is undergoing uniform circular motion. And the force applied to the satellite is, the big G, mass of the Earth, the mass of the satellite, the radius of the Earth, plus the altitude of the satellite. We are applying Newton's law of universal gravitation. That's the force on the satellite. But because the satellite is undergoing uniform circular motion, we can state that it's the force of gravity. It's is the centripetal force as well. Is mv square over r plus h. Can you picture that? Okay. R is the radius of the Earth. I'm asking the altitude of the satellite. That's why I'm putting h there. Find its altitude, okay? That's why I'm putting r plus h there. So this equation is equal to this one. Okay, I'm gonna put it like that. Here you go. So you can understand mass times centripetal acceleration. Yep. And then I put the centripetal acceleration is this one here. It's this term, v squared over r. I'm gonna even put it another step. I'm gonna put lowercase r. Okay. V squared over r. So what you have to equal here is gonna be this guy with this guy. Right? So where is the question is where is the period of rotation there? We don't have the period of rotation yet here in this formula, right? But we can get it very easily. Let me copy and paste. Here we go. I'm going to stick to this alone. What we're going to do, we're going to cancel this r plus h with this r plus h here. And we're going to cancel this little m with this little m here. Here you go. Now the period of the satellite around the Earth is right in here, inside V. Remember that I told you that it is uniform circular motion, right? So this V that you see here is in reality 2 pi r, no, sorry, 2 pi little r, the radius of this circle, divided by the period. That's what it is. Okay? And let's go ahead. Spell out of little r is, right? We had done that before. Little r is big R plus h. That's what we want to know. We want to know this guy. I'm gonna boldface it. Boldface here and boldface it here too. Okay. Let's go the next step. The next step is 4 pi square. The r plus h becomes square. And the t becomes square. Like that. And so the important relation that you take from this derivation is this one right in here. And we can elaborate it a little bit more. Okay, this r plus h go to the other side, becomes cube. Let's continue the derivation. Here we go. We want to know h, the one that's both faced in there. I'm gonna pass everything that I already know, everything that I can pass to the right, to the left side, everything that I already know to the left side. We're not there yet. Here we go, this one. 4 pi square. Algebra, right? I'm gonna solve for h now. In order to solve for h, I must take the cubic root on both sides. Let me see how we can get the square root here. There is a, I believe that's the one. Yeah, that's the, but I don't like this square root. Do you like this square root? I don't like it. Okay, I'm gonna do it in the long way. It's this one right here that I want. Radical. Okay, here you go. And I'm gonna put the radical 3 here. I'm going to, it's convenient, right? It's better to put what we do not know on the left side and what we do know on the right side. That's what it's better to do. And now we can finish. H is going to be R. Oh, no, it's not R. Is this square cubic root minus R. And now we can go ahead and plug in our equation. We're going to do that using Excel. Let's do that. Here you go. Excel right in here. I already have most of the parameters here in this spreadsheet. All I have to do is to calculate H, right? H is going to be, let's see, is big G, big M. Let's see what else. Did you memorize the equation? Period square. Oops. I gotta write down the period. Oh, come on, man. Yeah. Period square. I'm gonna put it right in here. Period square divided by 4 pi square. And then I'm gonna close this one as well. And what else I have to do? I have to subtract this value from the radius of the Earth. That's already here. I didn't put the period yet. I'm gonna put the period now. But the period, remember, has to be in seconds. The H is going to be in meters. It's 24 hours, right? 24 hours is the period of the satellite. But you want to have everything in seconds. Okay, 24 hours have 60 minutes. 1 minute have 60 seconds. 86,400. Why am I getting negative? Something wrong here. Let me see. Oh yeah, I forgot to put the cubic root here. Let's see if we get it right now. Oh no, I made a mistake here. I put a G instead of H. Okay, see, that's what we call troubleshooting. Okay, so what you end up getting here, I'm gonna put that in kilometers. We get this big number in meters, right? Divide that by 1,000, and we get that in kilometers. It's 40,000 kilometers. It's 35,900 kilometers. 36,000 kilometers. 36,000 kilometers from the surface, not from the center of the Earth, right? From the center of the Earth, I'm gonna put R here in kilometers. From the center of the Earth is going to be this value here plus 6,000 whatever. So a very good way to memorize this, the distance, the radius. Oh, something wrong here. Okay, I know what's the problem. I'm gonna divide this guy by 1,000. Okay, now we got it. Yeah, a very good ballpark number for the distance of the geosynchronous satellite to the center of the Earth is 40,000 kilometers. Here he's telling us it's 42,300. But that's a very good ballpark. Okay. So those satellites have applications, right? They are used for telecommunications. Geosynchronous because it's synchronized with the rotational motion of the Earth. And this satellite was invented back in the 50s. Invented, between quotes, by a science fiction writer called Arthur Charles Clarke. he published a science fiction novel. Nobody had figured that out at the time, but he figured out that if you put a satellite at this altitude, it would be very useful for telecommunication signals, because now you could have a satellite only at one spot in the sky, and you could point your antenna. Your antenna didn't have to keep on moving in the sky following the satellite. All it has to do was pointing to a single spot in the sky, just like you have your parabolic antennas there at home, right? If you have a satellite service, they put a parabolic antenna there at the top of the house. The antenna doesn't keep on moving to follow the satellite, right? That's because the satellite is in geosynchronous orbit. It always stays at the same spot in the sky. So all they have to do is put their, static antenna, parabolic antenna, aimed at that specific region of the sky where the satellite is located. Okay? And you have a simple system that doesn't require moving parts. What time is that? 5:48 already? Okay, so let's take attendance. Excel. I'm going to pause this recording. Good. So let's see what's going to be next. Okay, we did a geosynchronous satellite. Here we go. We can also find the orbital velocity of the International Space Station at an altitude of 350 kilometers. It's possible to do that. So all you gotta do, go back. Here you go. We go back to that derivation that we got before, right in here. Okay? So, but it's gonna be a little bit simpler now, because it's the same equation. It's exactly the same equation, like this one here. But now little m is going to be the space station mass. Okay, and the velocity here is going to be the velocity of the altitude of 350 kilometers. H is going to be 350 kilometers. So for V. So I'm going to use this equation here. Gravitational force is equal to centripetal force. That's what it's all about. Okay, so here you go. Speed, orbital period. Orbital speed of the ISS. Here you go. And we can take the square root. Let's see how I'm gonna do that. The easiest way. Yeah, I'll put this one here on the other side. That's how we find the speed. Big G, big M divided by RH. Here's 350. Let's go to Excel. Excel, let's see, speed. Go. Square root. Big G, big M, divided by the radius of the Earth, plus 350,000, because it is in meters. And then I know those things by heart, by the way, folks. The speed is around 8 kilometers per second. That's what you're getting here, 7.7. Don't forget that's meters per second. Okay, meters per second. Anything else? One more, and we can also find the period. Let's see here. Find out the orbital period, not the orbital velocity. No, I found the orbital velocity. Now let's find the orbital period. The orbital period ended up being like 1 hour and a half. Going around the world in 1 hour and a half, 90 minutes. Okay. So there was this novel, science fiction novel by Jules Verne, Let me get. Everybody should know that, right? Because they made movies about that. Jules Verne novels. He wrote several novels. He wrote Journey to the Center of the Earth. He wrote about that submarine Nautilus, right? And then he also wrote about going around the world in 90 days, right? Oh, I don't want that. I want. Let me get the name of the book. Oh, what the heck's going on here? Yeah, here we go. Jules Verne. He was a Frenchman. So let's see if I can find the name of the book. Why am I saying that? Oh, there's something real. Oh, 80 days. Okay, here you go. That's the name of the book that I was looking for. It's not 90 days. It's 80 days. Books around the world in 80 days. Okay. At that time, in his time, going around the world in 80 days was a major feat. Okay, 1872. Think about that. If you know this story, everybody knows this story, right? The two gentlemen made a bet, and he said he could go around. This guy said he could go around the world in 80 days. The other guy said he doesn't believe that. He's gonna lose the bet. He bet his whole fortune to do that, and he did exactly in 80 days. He almost lost the bet. So there was this writer that made a comparison between this book here. Look, Julius Verne said that it was very difficult to go around the world in 80 days. And yet nowadays, with the space station and the spacecraft up there, astronauts goes around the Earth in 90 minutes, not in 80 days. In 1 hour and a half minutes, when we can calculate that, okay? We can calculate that. We're going to do that right now. That's the orbital period, the uniform circular motion, and we use exactly that same formula that we used before, right in here, 2 pi over t. We want to find out 2 pi r over t. We want to find out the t, the period t. 7 go v, 2 pi r over t, like that. Let's not forget that r is big R plus h. Ooh. Here we go, big R plus h. We want to find out this guy right in here, right? So solve for t. That's how we do. And then we use Excel to find out what t is. We already have v, right? 2 pi r plus h divided by v. Let's go to Excel. T here. Go in seconds. 2 pi r. Here you go. That's not the one we want. What am I doing here? Let's see. Here you go. That's what I want. This one. Yeah, and then I have to sum 350,000. Okay, good. 2 pi r over v. Hopefully I get it right. It's supposed to be around, is that right? Yeah, that sounds right. In seconds, I'm gonna change that to minutes. See, 91 minutes, right? I'm gonna put it in a better format so you can see the numbers better. In number format instead of, yeah, see, 91 minutes. That's how long it takes for the space station to go around the Earth. To go around the Earth, no, it's to complete one orbit, right? It's not exactly to go around the Earth. Just like your geosynchronous satellite, right? Your geosynchronous satellite completes one orbit in 24 hours, right? But it never goes around the Earth because it always stay at the same spot, right? The same relative spot. Makes sense? It always stay at the same relative spot with respect to the Earth. So it doesn't go around the Earth. It's the same thing for the space station. Complete a full orbit in 91 minutes, which is, go completely around the Earth, maybe around that, maybe a little bit less, because the Earth is rotating a little bit longer, right? Because the Earth is rotating while the space station is going around, but the space station is going faster than the rotation of the Earth. One more. Let's see. I think I'm going to skip now to potential energy. Otherwise, we don't have time to finish everything 6:20 for this chapter. Yeah, here you go. We're going to start potential energy now. Gravitational potential energy. Okay. And that should be the last thing here in this chapter. Yeah, but before we go into that, let me just give you a qualitative idea of how to put an object in orbit. People came up with a very nice explanation. After this idea of putting an object in orbit, this idea that I'm going to show to you, see here, came from Newton himself. Okay, here you go. How we can put the space station in orbit? How can we put a rocket in orbit? Here we have a very qualitative idea that's very nice to understand. So think about, I decide to build a very tall mountain. Yeah.
Is this the falling and lifting one?
What do you say?
Falling and lifting.
Falling.
And lifting.
Yeah, it's something like that. Here you go. So go ahead, build a big mountain, right? A big tower, a big building, a very tall building. That was an explanation that Newton gave in his book, Principia. And then you go ahead, put a cannon there at the top of this tower, and you fire the cannonball. Okay, so eventually now the cannonball is gonna impact the Earth right in here, right? And we are doing that at the equator, by the way. This explanation works only if you do that in the equator. Here is the North Pole, okay? Then you want the cannonball to go further than that. And then what do? You put more gunpowder there, right? More juice, and the ball impacts the Earth further from the point of launch, right? Put a little bit more juice there, and then you have an intercontinental ballistic missile there. You can bombard anywhere in the Earth's surface. That's what intercontinental ballistic missiles are all about. You launch from one place, and it can impact a point in the Earth that half away from the circumference of the Earth. But then, okay, look at the vector velocity here, right? Look at the vector velocity here. Longer and longer, right? But then there is this sweet spot, the sweet spot velocity that if you get it right enough, I should have increased this velocity vector here. Here you go, like that. If you get it the right velocity, the object is no longer going to impact the Earth. It's going to follow the surface of the Earth, the circumference of the Earth. Okay, so look at that. Let's do that again. Here you go. Small velocity, larger velocity, larger velocity, even larger velocity. Okay? It never, the object is in free fall, forever in free fall. Okay? This velocity is the orbital velocity that we calculate there for the space station. It's approximately 8 kilometers per second. It's more like 7.7. Okay? It's very difficult to achieve this type of speed. It's 25 times the velocity of the sound. 25. Mach 25. It is already difficult to break the sound barrier. It's not everybody can do that, you know? Only government with supersonic jets can do that. And now Elon Musk, right, with his rocket. It's very difficult to achieve this velocity. It's so difficult that not every country in the world has this type of technology to do it. There are very few countries in the world that have. United States, Russia, Ukraine, the Europeans, the Japanese, even the Brazilians don't have it. Don't have this type of technology. They tried to do that. They blew up, got people killed. You know. So that's how you do it. You you don't have to propel upwards. You can propel in the horizontal direction. Okay. You can propel it in the horizontal direction, provided the speed is fast enough, and you're going to circle the Earth. Okay. And the speed is 8 kilometers per second. So that's an important point to have in mind. Okay, now we can start talking about potential energy. Potential energy, gravitational potential energy. There are two types of potential energy that you know. Okay, two types of potential energy that you already know. Two types of potential energy you already know. Okay, potential energy due to mg, right? The gravitational, here you go, I'm going to write that down. Gravitational potential energy. Oh, by the way, is the gravitational potential energy nearby the Earth's surface. Okay? Which is given by the force mg. The potential energy turns out to be mgy. If the force is mg, there's this other elastic potential energy. And the elastic potential energy is given by Hooke's law minus kx, with a potential energy given by half kx squared. Superscript. And now there is also the another gravitational potential energy that's valid for any altitude. There is also gravitational potential energy valid for any altitude. That's the one derived from Newton's law, universal law of gravitation. Let me get the equation because this one here. Okay, we do have a gravitational potential energy for this force. And by the way, this force is a conservative force. Only conservative forces have potential energy. Okay, I'm gonna put that little r here, and it's the distance from the center of the Earth. Here we go, right? So if you put it in vectorial format, let me see vectorial. Oh no, no. Yeah, okay, good. Here you go. You get like that, vectorial format, because it's attractive force. we must have a negative sign here. And let's not forget to put, no, hat. Oh, didn't do it. Let's try it again. Yeah. Huh, why is it doing that? Strange. Huh. Okay, let's try it again. It's not supposed to do like that. Ah, okay, now you did it. Did the way I wanted. Okay. Altitude. And I'm gonna do the step-by-step derivation just like I did before for the other ones. How we start? We start with the potential energy difference. Right? Not what I want. So let's go to the definition of potential energy difference. Definition of potential energy difference is delta U equal to minus that integral. Nope, not what it is. Oh man, what a mess. It's minus the integral. I'm gonna get the integral there. Hang in there, folks. Gotta go here to the long way. It's a line integral. Remember potential energy difference? Is a line integral of the conservative force is minus the work done by the conservative force. I don't want this dot. Jesus. Ah, they have this odd thing. Here goes, let's try it. Ah, I hate that. Why is it doing that? Let's put, look at my keystrokes. Here you go, that's the one I want. Here you go, that's the one I want. And now I'm gonna put the vector dr. That's the definition of potential energy difference. Here you go. Oh, and there's more. Here you go. I'm going to illustrate here for you. So what do you do? What we're doing, the potential energy of the Earth and another object is going to be minus the work done by the gravitational force when you move the mass from one place to another. That's how we do it. That's how we calculate it. It's initially at position R0 and ends up at position RF. Okay, so I gotta put that in my equation. Here should be R0, R0, and RF. Here you go, RF like that. And then we are doing the work done by this new gravitational force that's written different. It's a more generic one. Okay, so what we're going to do, I'm going to substitute right in here. Okay, here you go. Let's make sure we put that in parentheses so we do not get confused what sign goes where. Here you go. Right? We go the next step. The next step, this negative sign cancels out with this negative sign. Not only the negative signs cancel out, but the constants can be taken out of the integral. And we have the inverse of the square. And now we have to worry about this dot product. But everybody knows how to do that. When you r hat dot with dr vector, it becomes just the integral of dr. See that? And now my limits here that were vectorial limits become scalar limits. Becomes r naught rf. We have to get this integral. The integral of the square is going to be what? Everybody knows this integral, right? Becomes minus divided by r, and then we apply the limits. Let me see how I'm gonna do that. No, doesn't work. Don't want that. It's right in here. Yep. I'm gonna put. I wanna do it in a different way. Here we go. I'm still gonna learn how to get this keystroke right here. The keystroke is much quicker. Single brackets. Take your time, take your time. It's not showing anything. Let's see here. Okay, I want this guy. This is the guy I want. Man, my eyesight is getting terrible. Yeah, I got it. This one here. Here you go. R naught. Hey. And then, yep, RF. And I don't need that anymore, right? Can I? What I'm gonna do, I'm gonna put in the next line. What time is that? 6:36. We still have time. Come on, man. Oh, yeah. Gosh. Even Word is taking a long time. Okay, here we go. We're gonna apply the limits here. I got okay, the first one go like that. The next one should be R naught. Right? Go. That's my potential energy difference. I'm going to swap the signs here. This guy is going to become negative. This guy is going to become positive. And then I'm going to commute those two terms. Oops. It comes like that. Okay. That's what happens when we move one mass from one point to another. And let's not forget what this delta U means. This delta U means final potential energy minus initial oh, why did you do that? Yep. Final potential energy minus initial potential energy equal, go, that. There it means. We are going to simplify the notation by dropping the F subscript. Okay, and we made U as being my generic potential energy, my final potential energy, and R my final position. Okay, so we're going to do the next step, next thing. Okay, next thing, we define, a initial potential energy. We define, let's see, initial potential energy that is not an initial potential energy, a reference. Let's put it this way: a reference potential energy that we define a point. Let's see how I'm going to write that down here for you. There's a better way of writing it down. Next thing, you know. Okay, we're going to do the following. Here you go. Next step. Next step. We will get our potential energy difference with respect to a point, to an initial point, with respect to an initial point, are not located at a very large distance. Or, we go, are not is going to be very large distance. Is going to be, let's see, okay, let me see if I can remember. Right arrow, no, right arrow, nope, doesn't like it. Okay, I gotta do it from the long way. For are not going to very large value and then infinity. Oh no! Nope. No. Go. Infinity. Nope. Didn't like it. Okay. Gotta go the long way, the long route. Oh, infinity. That was gonna be the reference point that we're gonna take. Why is that? Now, if you put r not equal to 0, this guy here is not gonna lead us a finite number, right? So we have to choose a different point. The most convenient point that we can choose a reference is a point that's very far away from the Earth at infinite distance. In this case, what happens? It happens that this term cancels out completely, right? And you get this potential energy difference. Then we take another step. Then we take another step. We choose our U0 as being the origin of our potential energy axis. Okay? Or we make U0 equal to 0 as well. And let's see if it's mathematical consistent or not. Let's see if it's mathematical consistent or not. When we do something like that, here you go. We get a potential energy, not a potential energy difference, but a potential energy that's now equal to minus G big M small m divided by R. Is it consistent with this imposition here. With this imposition here. Let's see if it's consistent or not. Okay? U naught is the value at U when R goes to infinity. Does it make sense? If we put R equal to infinity here, what do you get for U? We get 0, right? So this relation makes sense. It's mathematical consistent. First, we choose a reference point to take our potential energy difference. And by analyzing the potential energy relation, we find out that we cannot choose this point as being R not equal to 0. The center of the Earth is not going to work, because if I put 0 here, this guy going to go to infinity. Okay? Then we look at the other end. At the other end is, what if R naught is infinity, has an infinity value? Okay, it does lead to a mathematical number, because this value here goes to 0. Then the next step is, what is the value that we are going to assign to U naught? That's the next step. Okay, so we decide to assign U naught as being equal to 0. When we assign U naught equal to 0, we find out that the final result is mathematically consistent with this condition and this other condition here. Okay? So it works. And now that we have the potential energy for the gravitational potential energy, we can start talking about solving problems using the concept of conservation of energy. Okay, and what time is that? 6:45. We have 5 more minutes. I will try to do that right now. But this time, let's see here. I'm not even gonna write, because I did everything here. Okay, I did everything here, even more, but we don't have time to cover all of that. So what do we do here? See, RA going to infinity, all that stuff. Let's see. I'm going to skip that as well if you want to read. Okay, energy in planetary motion. Okay, I'm going to do an example. We're running out of time. We cannot. We're going to find out. We already found out the orbital speed. Okay, we already found the orbital speed. Now what we're going to do? We're going to find the escape speed of a particle from the surface of the Earth. Okay. Escape. What escape speed means? Here you go. Let me give you an idea here. Qualitative idea. You already know how to put an object in orbit, right? Here you go. You just propel it fast enough so you go into a circular orbit. But if you keep on propelling even faster, the circular orbit becomes something else. The circular orbit becomes an elliptical orbit. See? One elliptical orbit here, another elliptical orbit here. And then, if you go even further, something else happens. You no longer have an elliptical orbit. You no longer have a closed orbit. The particle doesn't go back to its initial point. What's going to happen? If you propel your particle fast enough at speeds greater than 11 kilometers per second, and we can calculate that, initially the particle goes in a parabolic orbit and never return. That's an actual result that we get. And if you go above 11 kilometers per second, the particle goes in a hyperbolic orbit. Okay? So we have circular orbit, elliptical orbit, parabolic orbit, and hyperbolic orbit. It all depends on the initial energy of the particle, the launch energy of the particle. Initial energy of the launched particle. Okay? So how do we get the escape speed? How do we get to find this 11 kilometers per second? Well, we do energy considerations. Okay? So we start with a potential energy plus kinetic energy right here at this point, and a potential energy plus kinetic energy at a point that's infinitely distant from the Earth. You get the idea? So here you go. I'm gonna draw here for you. Here's the Earth. right? Here is your projectile. Here you got the top of a big mountain. Here's your super cannon. Okay, you're going to propel your cannonball, and you wanted this particle to move away from the Earth and never come back. Very far away from the Earth, what's going to happen? You know, as the particle moves away from the Earth, its speed is going to bleed out little by little, right? That's intuitive, right? If I launch this pen upwards, away from the Earth, little by little the pen loses kinetic energy but gains potential energy, right? Here's the same situation. As the particle moves away from the Earth, further and further away from the Earth, the potential energy becomes less negative, which means your potential energy is increasing. Consequently, the kinetic energy must decrease, okay? Potential energy increases, kinetic energy decreases. Okay? When the particle is very far away from the Earth, and a distance that's infinitely distant, what's going to happen to the kinetic energy? It's going to become zero. Okay? So here you go. At this point, you have kinetic energy plus potential energy, initial kinetic energy plus potential energy. Very far away from the Earth, you have final kinetic energy, final potential energy. Very far away from the Earth, at r equal to infinity, potential energy is equal to what? Zero, right? Remember that? Since the particle is decreasing its speed that goes further and further away from the Earth, at a point that is infinitely distant to the Earth, the particle is going to be at rest as well, asymptotically at rest. Okay, so now we have the situation. Initial kinetic energy plus initial potential energy is equal to zero, must be equal to zero. The initial kinetic energy must be minus initial potential energy, which is equal to big GM, G big M divided by R. That's the radius of the Earth. Here is mv naught squared. Okay. Let me see here. Is that right? And we lost the potential energy. We still have a name there. Let me double check. Yeah, we still have a name there. And use the M here. Okay. Big G, big M, is small m R. M cancels this M. V naught squared is 2 big G, big M over big R. You take the square root of this term. So we have 2, right? 4 big G M for the mass of the Earth and the radius of the Earth. We get approximately 11 kilometers per second. Okay, that's how you get this result. And we are done with this chapter. The exam is going to be, let me see here. What chapter is this one? Is that 11?
It's chapter 13.
13? Okay, 13, thank you. Yeah, it's going to be at least 13. Okay, so let's see what happens on Tuesday. Maybe we will add it, maybe we will not add. Let me check here. That's the version here of the syllabus. No, that's not this one. It's going to be at least 13. 12. This one here. Here we go. We finish. Like I said, I usually take three meetings for this chapter, but because we're running out of time, you know. Yeah, 13. Remember, it's the end of chapter 10, right? It's the end of chapter 10. So I'll give you a break. Let's do that at end of chapter 10, 11, 12, and 13. That's enough, right? 3 chapters and a little bit of chapter 10. It's going to be the same deal as before. Make sense?
Yeah.
Okay. And then we leave the other 2 for the final exam. So let me save that, and okay, we can stop now and we can meet there upstairs.